Now again, the hypothesis test that we're using here, or there's actually two different hypothesis tests, and the book talks about the difference between them. One is called the z-test, and the other is called the t-test. The purpose of both of these tests is to test a claim about the mean of a single population. Now this word single here is very important because later on we're going to talk about tests where we compare two different populations. And again, the book talks about more of the details between these, but for our purposes we can just say that if we have a large sample, large meaning n greater than 30, then we use the z-test. If we have a small sample, small meaning a sample size of less than 30, then we use the t-test. Now the worksheet in the workbook chapter 7 takes this into account, and takes the sample size into account when determining what type of test to use. So we don't have to worry about which type of test to use. The worksheet takes care of all that for us. Now for each one of these hypothesis tests that we'll talk about, they all have certain requirements that have to be met. Now we're not going to worry too much about the requirements, but we do want to be aware of the fact that we can't simply blindly plug any set of data into any formula and expect to get valid results. We may get results, but they're only going to be valid if certain requirements are met. And in this case we have two requirements. First requirement is that the sample is random. That's always a requirement. We have to have a random sample. If we don't have a random sample, then we just can't do enough number crunching to salvage the data. So this is always a requirement. The sample is random. And then second requirement is that either the population is normally distributed or we have a sample size of bigger than 30. Now this requirement of having a normally distributed population is something that we'll talk more about in chapter 10 when we talk about non-parametric tests. We talked about normal distributions a little bit earlier on in the semester. But just be aware that normal distribution is extremely important in many of these hypothesis tests. Now let's do one last example here that's going to illustrate a two-tailed test. And so in this scenario, this is example 7.2 from the book. In 2002, the mean total cholesterol level for all adults was 203. Again, where this number of 203 comes from, we won't worry about. We'll just take this number for granted. Okay. So a question that a researcher might ask is the current mean total cholesterol level for all adults different than 2003? Now we're not asking has it increased or has it decreased necessarily. We're only asking is there a difference? Is it different than it was in 2002? Okay. So the claim or the research hypothesis that we're going to make is that the mean is different than 2003. It makes sense that things have changed since 2003. Now we're not sure if the mean has increased or decreased. We're just going to claim that it is different. Okay. So the parameter, what it is we're making a claim about, is mu, the current mean total cholesterol level for all adults. Again, we see this word all here because we're making a claim about the large population of all adults, not just the few in a sample. Okay. So now we need to set up our hypotheses. Well, let's make an observation. Remember, the null hypothesis is the statement of no change or no difference. So if the current mean is not different than it was in 2002, then mu would be 203, the amount that it was in 2002. So the null hypothesis is the statement that mu equals 203. Now the claim or the research hypothesis is that mu is different than 203. And so our alternative hypothesis is going to be the statement that mu is not equal to 203. Okay. So here's the data as given in the book. So here we went out and we measured the total cholesterol of 3,310 people. We got a mean level of 200.3 with a standard deviation of 36.8. Now, this number here is the sample mean is different than 203, so our data appears to support the claim, but as always, this data do not prove the claim. This number here of 203 is an estimate of mu, or population mean. It appears that mu is different than 203, but we need to measure just how strong that support is. So we'll use our same worksheet to calculate the test statistic and the p-value. Here's mu naught, the number that appears in the null hypothesis. Here's our sample data. Now in this case we have a two-tailed test, and that's because our alternative hypothesis was the statement that mu is not equal to 203. And so here's our test statistic, and here's our p-value. Now notice here that we've got a rather large sample, and so this is, we're using technically a z-test here, but for our purposes not terribly important. So there's our p-value of 0. So we interpret that p-value in the same way as our other tests. Compare that number to 0.05. In this case, our p-value is much less than 0.05, so our conclusion is to reject the null hypothesis in favor of the alternative. And so we would say that our data support the claim, or stated another way, there appears to be a statistically significant difference between the current mean and the mean in 2002, which was a mean of 203. So let's just kind of summarize how we state our conclusion as all these different hypothesis tests. So we look at this number called the p-value, and if that p-value is small, meaning less than 0.05, then we reject the null hypothesis in favor of the alternative. So our conclusion, in less technical terms, is that the data support the claim, or stated another way, that the data support the research hypothesis. If we have a large p-value, meaning bigger than 0.05, we do not reject the null hypothesis and conclude that the data do not support the claim, or state another way, that the data do not support the research hypothesis. So this is the basic way that we're going to state our conclusion in all of our different hypothesis tests. If we have a small p-value, then we say that the data support the claim. If we have a large p-value, then we're going to conclude that the data do not support the claim.